Bayes theorem. This is a very famous formula from probability, or more than a formula, the concept of that has to do with the Bayes theorem. It's very famous and important in probability. But how this works? Well, first, let me introduce other formula first. That is called the total probability law. If we have a sample space and we have A1, A2, and up to AN are events, of S such that the intersection of any two events is the empty set for if we have a finite amount of events, finite amount of events for a given sample space, such that when you take two of them, their intersection is the empty set, and if you compute the union for all these events, and so on up to n, this means that the union, you put together all of these events, you have the sample space, then we call the collection A1, A2, and so on up to AN a partition of S. So if we have a sample space, we have a finite amount of events. Actually, it could be infinite, but for the purpose of this, finite is enough. And then we have each of these two. They are empty. I mean, their intersection is the empty set, and the union of all the events in the sample space. Then we say that this is called a partition of S. How do we know we have a partition for a sample space? We have a collection of events such that by taken by two, they are the empty set, or they have nothing in common, and the union of them is the sample space. That is a partition. Now, based on these ideas, consider any event. Remember that if we have an event, then by definition, an event of the sample space is only what? It's only a subset. Then based on this, if I do the intersection of the event B with the sample space, it's going to be only the event B. B is the same as B intersection with the sample space, because the sample space, the event is inside the sample space. But if I have a partition of the sample space, let's say that we have a partition for the sample space S, so I can express this in the next way. I can express this as B intersection A1 union A2 and so on. And by following some properties for sets, this is the same as I can distribute each, I can distribute the event B with each of the events A1, A2, and so on up to AN. For example, I would have here B intersection A1, union B intersection A2, and so on. So notice B is the same as this. So that the probability of B, this is B, is the same as this, then the probability of B is going to be the probability of all of this. Is that okay? So, but all of this, notice, I have a union, each of these, B intersection A1, B intersection A2, B intersection A-N, all of them, they are disjoint, yeah? So by following the properties for a function probability, for a probability function, this is the same as the probability of B intersection A1 plus probability of B intersection A2, and so on. Or what is the same with the sigma notation, is the sum from 1 up to n of the probability of B intersection AI. Yeah? Now, we know that if we want to compute the probability of B given any event AI, by definition of conditional probability, this is the probability of AI intersection B divided by the probability of B. And if we solve for the probability of intersection, this means that the probability of intersection is only the probability of B given AI times the probability of B. Only multiply both sides times the probability of B. You will cancel this in the right side, and you are going to be multiplying times probability of B in the left hand side. So we have this. So probability of B is equal to this, but each of these can be computed in this way. So that I will continue here. Then the probability of B is equal to the probability of B given AI times the probability of B. And this is called the total probability law. Yeah, I know. Maybe some of you are saying, "Well, what are you doing here? You're using many formulas. You are not showing any example." Yeah, not yet. But this formula is important. I will try to explain one way to interpret or some ways to interpret this formula. So we can think of this in the next way. Let's say that a given event B has several causes, and the causes are the events A1, A2, and AN. The causes of B are the events A1, A2, and so on. So this formula, let's say that we have one event B, and then we know the causes A1, A2, and AN. I mean, the causes of the occurrence of the event B are A1, A2, and so on up to AN. Then this formula, then we can compute the probability of occurrence for B in terms of the causes A1 and so on up to AN. So this single formula that I have deduced here with this reasoning, with all of this reasoning, is it can be interpreted like that. The causes for a given event B are A1, A2, and so on up to AN. So this formula says, well, you can compute the probability of B in terms, the consequence in terms of the causes A1, A2, and so on. Oh, I'm sorry. I think I have made a mistake here. Notice probability of B given AI if this is correct, divided by the probability should be AI. I'm sorry for that. I will fix that. AI, AI. And here should be 2 probability of B AI. Probability of B is equal to forgot to put the sum. The sum from 1 up to n. Yeah, I'm sorry for that. So now, so the same, with this formula can be interpreted as we can compute the probability for a given, for the consequence B in terms of the causes AI. So that's why I mentioned before that this Bayes rule is interesting because it allows to compute many things that maybe they can be interpreted or thought as a paradox. For example, here we know that, I mean, what about if we want to compute probability of AI given B? This could be interpreted as probability of the cause given the effect or the consequence. Yeah, I know. Typically, we should be able to, I mean, maybe we are more interested in computing what is the probability of the effect given the cause. If a cause, if we have a cause, then that means that something has occurred and that has some consequences or effects. But an interesting question is what about if I want to compute the cause given the effect? I mean, it's like if the effect occurred, how can we compute the probability of the cause? Yeah, it's weird, right? But we can have a formula to compute this. And probability of A given B, we have a formula for this. I mean, it's only the conditional probability. It's probability of A I intersection B divided by the probability of B. Or what it is saying, since probability of B given I, AI, is equal to probability of AI intersection B divided by the probability of B of AI. I think the formula we have here. Yeah, I'm sorry. I mean, it is formula here. Oh, this one here. So I can write only for probability of intersection only this, right? Is equal to the probability of B given AI times the probability of AI over the probability of B. So I think we don't need this because we already have it here. So the probability of AI given B can be computed in this way. This is known as Bayes formula. But this formula can be also expressed in the next way. Probability of A given B is equal to probability of B given AI times the probability of AI divided by the probability of B. But we already know from the total probability law that probability of B can be expressed in this way, you see? So plug this in here to replace probability of B. And we are going to have the sum of the probability of B given AI times the probability of AI. And this is the same, it's the base formula. Only other way to express it. Base formula, base formula. It's like can be interpreted as you want to do you have the consequence or you have the effect, then you want to know, you want to know the probability of the cause, then you can compute it with base formula. All right, yeah, I know this was only about so far as to how to deduce all of this, right? And the motivation behind this. But now let's see of course some examples from the assignment on web work. It says in a particular country 3% of the population is HIV positive. A test for 3%. A test for HIV correctly diagnoses 95% of those who have the condition. Notice here, a test for HIV correctly diagnosing 95% of those who have the condition. So this looks like a conditional probability, right? But incorrectly diagnoses 4% of those who are not HIV positive as being HIV positive. A patient obtains a positive test result, apparently indicating the presence of HIV. Determine the probability that the patient is really HIV positive. Please round to 3 decimal places. So this is like the classic example. I mean, when you have a test, that is trying to diagnose a given disease, well, the test might be wrong. Yeah, it's a possibility. But what is the probability that you actually have the disease when you have a positive test? Of course, we can have the other mistake as well, that you have a negative test, but it results that the test is wrong and you actually have the disease. But here, let's focus on this. First, I'm going to label here H equal to HIV positive. So that the probability for H, or the proportion or percentage of H, is 3% or 0.03 because of this. Now, probability of positive tests, I'm going to use this positive test. Notice it says a test for HIV correctly diagnoses 95% of those who have the condition. Given that they have the disease in this case, well, they are HIV positive, 95% actually they have that. So here I will be using for positive pos given H is equal to 0.95. And the probability of positive given they don't have or they are not HIV positive, I incorrectly diagnosis 4% of those who are not. So how can I express this? If H represents the one that they are HIV positive, how do I represent, based on this, the one that they are not? Well, a complement. So it's going to be H complement. And this is equal to 0.04. So what is the question here? What are the determine the probability that the patient is really HIV positive? So we look for probability that the patient is HIV positive, in this case the probability of H, but given a positive test, you see? And in this case, I think we can take advantage of this formula. Probability of B given AI times probability of AI. Notice here H is going to be the AI and B is going to be pos. So we're going to have probability of positive given H times probability of H. And in the bottom, should be probability of positive divided by the probability of positive. Well, we don't have exactly that, but no problem. From the total probability law or this, it can be computed. Because notice, the sample space can be divided into the one that they are positive, I mean the ones who take the test, they're positive or they have the disease or they don't have the disease, H and H complement. So based on this can be computed like probability of positive given H times probability of H divided by the probability of positive given H times probability of H plus the probability of positive given H complement times the probability of H complement. Yeah. Probability of positive is this. So this is equal to what? Probability of positive given H is 0.95 times probability of H, 0.03, divided by probability of 0.95 times 0.03 plus probability of positive given H complement, that is 0.04, times probability of H complement. Here, what is H complement? If H is 0.03, H complement is going to be 0.97, right? 1 minus 0.03, 0.97. And there you have, if you compute this, you can verify that the answer is 0.423. So what is the probability that the person who has a positive test actually has the disease or the HIV? According to the data, 0.423. Okay? Perfect. Now, other example, the U.S. National Highway Traffic Safety Administration gathers data concerning the causes of highway crashes where at least one fatality has occurred. One fatality has occurred. From the 1998 annual study, the following probabilities were determined. BAC is blood alcohol level. And then notice here we're given some conditional probabilities. You see? BAC between 0.01 and 0.09, given crash with fatality. BAC equal to 0, given a crash with fatality. 0.626, this 0.339, and probability of BAC is greater than 0.09, given a crash fatality is 0.053. Suppose then, well, we are given, actually I can write them down right now. I'm going to label this as probability of A1 given B is equal to 0.626, probability of A2 given B is equal to 0.339, and probability of A3 given B is equal to 0.053. B, of course, is crash with at least one fatality. Which fatality? And we have this condition probabilities. This A1 is BAC equal to 0, A2 BAC equal between 0.01 and 0.09, and A3 is between, greater than 0.09. That okay? So I hope there's no confusion. A1 BAC equal to 0, A2 BAC between 0.01 and 0.09, and A3 greater than 0.09. So we have this information. And what else? It says, suppose over a certain stretch of highway during a 1-year period, the probability of being involved in a crash that results in at least one fatality is 0.012. It has 0.012. So other information for probability. So I think this goes probability of at least one fatality. So this means that this probability of B. Probability of B is 0.012. And then it continues. It has been estimated that 12% of all drivers, while their BAC is greater than 0.09, so it's for A3, 12%. So this means that probability of A3 is 12% of 0.12. Remember that A3 is BAC greater than 0.09, so it says here 12% of while their BAC is greater than 0.09. Determine the probability of a crash with at least one fatality. If the driver drives while legally intoxicated. Legally intoxicated means BAC greater than 0.09. So essentially here we look for the probability of fatality, B, because of this, at least one fatality, given the person is intoxicated. That means BAC greater than 0.09, and BAC greater than 0.09 means A3. So given A3. And we know this is the same as the probability of B intersection A3 from the probability of A3. Again, from the formula of Bayes, we can take advantage of this. This is only the probability of A3 given B times the probability of B given the probability of A3. So in other words, we have a probability of A3 given B this, 0.053, times probability of B, that is 0.012, and they divided by probability of A3, that is 0.12. And if you compute this, you are supposed to get the answer, this one, 0.0053. So the probability of having a crash with at least one fatality, if a person is totally intoxicated, is 0.0053 or approximately 0.5%. Very well. One more example. Bad gums may mean a bad heart. Researchers discovered that 82% of people 82% of people who have suffered a heart attack had a periodontal disease and inflammation of the gums. Only 33% of healthy people have the disease. Suppose that in certain community, heart attacks are quite rare, occurring only with 12% probability. If someone has a periodontal disease, what is the probability that he or she will have a heart attack? All right. First here, H is going to be heart attack. Heart attack. And D is going to be periodontal disease. What do we know from here? We know that probability of D given H is equal to, how do we interpret this? Probability the person has periodontal disease given a heart attack. That is 0.82. You see that? 0.82% of people who have suffered a heart attack, given they suffered a heart attack, they had periodontal disease. So it's 0.82. Here, periodontal disease given no heart attack is what? Yeah, I know it's confusing, right? Because it says only 33% of healthy people. Healthy people doesn't mean necessarily that they don't have a heart attack, right? But we are interpreting like that. So healthy people is going to be the complement for heart attack in this exercise. So in this case, it's going to be 0.33. Yeah, I know. You think the redaction is confusing? Yeah, I think so. But this is the way to work with this problem. Healthy people is going to be interpreted here as no heart attack. Now, suppose in a certain community, heart attacks are quite rare, occurring with only 12% of probability. So this means the probability of H is equal to 0.12, and the probability of the complement, of course, is going to be what? 0.88. So in the part A, we look for what? We look for the probability. Notice, pay attention to the question A. If someone has periodontal disease, that means that periodontal disease is going to be the condition. Has periodontal disease, what is the probability that he or she will have a heart attack? So heart attack. What is the probability of heart attack given a periodontal disease? And this can be computed with the base formula, that is probability of D given H. Notice how, if you try to remember this base formula, I mean, always you will start with a condition of probability. Is H given D, and here is the opposite, D given the inverse, that D given H. Times the probability of H and divided by the probability of D. But D can be computed by using the total probability law, this formula here. but from total probability law, probability of D is equal to the probability of D given H times probability of H plus probability of the complement D given H complement times the probability of H complement. So this formula becomes what? Probability of H given D is equal to the probability of D given H times the probability of H divided by probability of D given H times probability of H plus probability of D given H complement. I'm sorry. Probability of D given H times probability of H divided by probability of D given H times probability of H plus probability of D given H complement times the probability of H complement. Yeah, I know maybe you wonder, how do I know that probability of D is this probability? Well, notice H if we have the sample space, then let's say that we have the event H here. Necessarily the other part of the complement is H complement, right? So always a given event and its complement, they create a partition of the sample space. So I can try to express, by using the total probability law, the given event in terms of that partition of the sample space. So that's why I only wrote here, based on this, probability of the given event given the causes, so the events AI. In this case, the event B is D, and I express D in terms of the AIs, but the AIs are only H and H complement, only two in this case. Probability of D given H times probability of H plus probability of D given H complement times probability of H complement, and that's why we have this. And this equal this equal to 0.82 times 0.12 divided times by 0.82 times 0.12 plus 0.33 times 0.88. And if you do it, you're supposed to get this answer here, this one. Now, the part B is some of the same, but we have to modify some probabilities. Part B, it says, part B, if 36% of the people in the community will have a heart attack, what is the probability that a person with periodontal disease will have a heart attack? So part B, the same, but use probability of H equal to 0.36 and probability of H complement equal to, of course, 0.64. And when you compute it, you will realize that this is the answer. So the answer for the first, for part A, this one, The answer for part B, do the same. Do the same as I did for part A. Only change pH by 0.36 and the complement by 0.64. The rest of the numbers are the same. When you do it, you will have this answer. Is that okay? All right, that's all by now. See you in the next video.